Assalamualaikum and good day. This time around, we will be solving this equation. X squared d squared y dx squared plus x dy dx minus 4 y over x equal to 0. When x approaches infinity, since it's given here that x is near infinity, and then it is a regular singular point which the initial roots differ by 0, which means here it is case 2. That is R1 equal to R2, and we need to find the two series solution of this DE in terms of x up to the third term. That means A0, A1 and A2. That's the coefficient that we need to find. So for the solution, we need to use substitution z equal to 1 over x here, so that when x approaches infinity, z is equal to 0. Next, please recall that dy dx is equal to negative z squared dy dz, and also d squared y dx squared equal to 2z cubed dy dz plus z power of 4 d squared y dz squared. So next would be, we need to substitute dy dx d squared y dx squared in the given dE, which means we will have this equation. Substitute 1 over z for x and z for 1 over x. The reason is because z is equal to 1 over x, which means x is equal to 1 over z. So expand and simplifying the equation, we will have this new dE. Okay, we will be using this new dE from now. So since z equal to 0 is a regular singular point, we will be using Frobenius method. Therefore, here we go. We have y equal to summation n from 0 to infinity an z power of n plus r. Take note, this will be written as z, not x, okay? And then y prime will be differentiate y with respect to z. It is summation n equal to 0 to infinity n plus r an z power of n plus r minus 1. And y double prime is differentiate differentiate y prime with respect to z. We have n plus r minus 1 times n plus r an z power of n plus r minus 2. So we need to back substitute y prime and y double prime in our new dE. We have this equation, z squared times our y double prime here, and then z times y prime and minus 4z times y equal to 0. Next, as usual, we need to expand the equation. Okay, we have this equation, summation n equal to 0 to infinity n plus r minus 1 n plus r a of n z power of n plus r. As you can notice here, there is difference in the power because z squared multiplied with z power of n plus r minus 2 will be z power of n plus r. Here z times z plus n plus r minus 1 will be z power of n plus r. And here z times z power of n plus r will be z power of n plus r plus 1. Next will be shifting the index, which we equate to the smallest power here, z power of n plus r. So nothing will change for the first term and the second term because the power is already n plus r here. But for the third term, it will be summation of n equal to 1 to infinity a n minus 1 z power of n plus r. Since we need to minus 1 for every n in order to get a new coefficient here, factor here, that is z power of n plus r. Here it changed to n equal to 1 because n minus 1 equal to 0. So the summation will start at n equal to 1. Okay. So next, writing the initial equation. Initial equation is when n equal to 0. So that means we just consider this part only, the first and the second term. Okay. We have r minus 1 times r plus r times a0. So this part will be equal to 0 since a0 does not equal to 0. Here we have r squared equal to 0, where r is equal to 0, which confirm that it is case 2. Okay, next, determining the recurrent relation. So, our recurrent relation will start when n is greater than or equal to 1. So, here n plus r minus 1 times n plus r a n plus n plus r a n minus 4 a n minus 1 equal to 0. So, remember that the highest coefficient should be on the left. Hence, here we have a n equal to 4 over n plus r squared a n minus 1. Next, substituting. When n equal to 1, we have a1 equal to 4 over 1 plus r squared a naught. And when n equal to 2, we have a2 equal to 4 over 2 plus r squared a1. Here we need to substitute a1 equal to 4 over 1 plus r squared a naught, which will be new a2, 16 over 2 plus r squared times 1 plus r squared a naught. Okay, next would be solving the power series. We have y equal to summation n equal to 0 to infinity a n z power of n plus r. Expanding the summation, we will have this equation, and factorizing z power of r, our y will be z power of r times a naught times a 1z plus a 2z squared plus until infinite. Okay, next would be substituting r equal to 0 in y to obtain y1. So, y1 is equal to z power of 0. Substitute r equal to 0 in our equation. And here is 4, 1 plus 0. Here 2 plus 0. And here is also 1 plus 0. Okay. So, we have a naught in bracket 1 plus 4z plus 4z squared plus until infinity. Next, substitute z equal to 1 over x. We have y1 equal to a naught in bracket 1 plus 4 over x plus 4 over x squared plus until infinity. Okay, we are moving towards the last part, which is first calculating, determining del y over del r, which is y ln z plus a naught z power of r, and here would be 4 over 1 plus r squared. This one is negative 2 over 1 plus r. We obtain it by differentiating 1 plus the denominator here. So, z here plus 16 over 2 plus r squared, 1 plus r squared. And here we obtain by differentiating the denominator. Okay. We have negative 2 over 2 plus r minus 2 over 1 plus r. And here is z squared plus until infinite. And y2 is equal to del y del r when r equal to 0. So, it will be y ln z plus a naught z power of 0. And we do quick calculation. Substitute r equal to 0. We have 1 here because 1 plus 0 is 1. Here is 1. 2 plus 0 is 2. 1, 2. 1 plus 0 is 1. So, simplifying, we have y2 equal to y ln z plus a naught in bracket negative 8z minus 12z squared plus until infinity. And we substitute z equal to 1 over x again. We have y2 equal to y ln 1 over x plus a naught negative 8 over x minus 12 over x squared plus until infinity. That's all. Hopefully, this will help you to understand how to solve power series when x approaches infinity, and also at the same time solving questions on regular singular point for case 2. Thank you. Assalamualaikum.